Hi, hello, and welcome to our channel Practicals Learning. This channel is managed by myself, Purushothaman R, and my friend Anirudh Sharma. Please do like, share, and subscribe our channel and keep learning.
So today we will proceed further with our physical properties of haloalkanes, which is a common set of properties which we will have in all the chapters of organics. That is, next one we are moving forward with is physical properties of haloalkanes. What are physical properties? The properties such as boiling point, melting point, density, bond strength, solubility, all these are considered as physical properties. In that, first one we will go with boiling points of some haloalkanes. Like first A is if size is more, then boiling point is also more. For example, like this: Ri, Rbr, Rcl, Rf. This is the criteria where Ri is the size of iodine is more, so itself boiling point is also more. This is one. And the next is branching. Depending upon the branching, we will erase the thing. So depending upon the branching we have the classification for the thing. So where we are learning today about physical properties, and first one we had seen the boiling point. In that boiling point, if size is more, boiling point is also more. For example, Ri, the iodine size is more, so Ri, Rbr, Rcl and Rf. So this is the thing. The next is branching. If the hydrocarbon branching is more, then boiling point will be less. If branching is more, boiling point will be less. So for example, N-butyl bromide, and it is more than secondary butyl bromide, and it is greater than tertiary butyl bromide. That is, N-butyl bromide branching is less, so itself it is having boiling point more. So N-butyl bromide branching is less, so itself it is like this: butyl bromide is CH3, CH2Br. It is N-butyl bromide, and secondary butyl bromide will have my branching. So this will be attached to like this, this thing. The carbon attached will have two alkyl groups attached to it, and that goes on like that. So branching, if it is more, boiling point will be less. So next physical property we will move, that is bond strength. That is bond strength. First is boiling point and next one is bond strength. Next one is bond. Next is bond strength under the physical properties, that is bond strength. What is bond strength? The bond between like this CC bond, the bond strength, how much strength it is there, so that is bond strength. So that is bond strength. If it is in case of haloalkanes, if it is in case of haloalkanes, if the size is less, if the size is less, bond strength will be more. It is a common sense thing. Size, if it is more, bond strength will be less. You cannot hold the so much big size if you itself is a small group of atoms. So it is a common thing wherein size, if it is more, bond strength will be less. Size, if it is less, bond strength will be more. That is like this. CH3F, size is less, so CH3Cl, CH3Br and CH3I. So my iodine atom is having more size, so itself it is less bond strength. So that is the bond strength. That is the second property under physical property. Next thing is solubility. Solubility. What is polar thing is, polar means it is having difference of charge. If it is having difference of charge, that should undergo solubility, means that should be soluble in water. But in case of haloalkanes, that doesn't work out. The haloalkanes, though polar, charges, if charges separate, though they are polar, they are not dissoluble, that is soluble in H2O, in water. Why? Because they do not form, they are incapable of forming hydrogen bond in water. This should form hydrogen bond in water, and then itself it is said to be the haloalkanes are soluble. But it is not forming hydrogen bonding, so therefore my haloalkanes are not soluble in water, because my haloalkanes, though polar, they do not form hydrogen bonding in water, so itself they are not soluble in water. This is the solubility property of haloalkanes. Next is density. What is density? We all know that mass by volume, and that plays a important role in sinking or floating. So my density order, how will my density order, it is a fourth one, okay, how will my density order changes in case of haloalkanes? My density order will be there. If size is more, then mass is more. So the same in case of boiling point. The same in case of boiling point. Ri, Rbr, Rcl, Ri. So my Rf. So my Ri will have more density, same as the boiling point. And the last final property of haloalkanes, physical property, is that they are dipole moment. Dipole moment increases. Dipole moment increases as the, see here it is an electronegative atom, it is. So dipole moment increases as my electronegativity of the halogen atom increases. My dipole moment increases as the halogen atom electronegativity increases. So these are the 5 physical properties of haloalkanes. Next, we will move forward with the main topic of the lesson, the chapter of every chapter, that is chemical properties or chemical reactions of haloalkanes. What are the reactions? We will see that. Chemical reactions. I will study many type of reactions under this haloalkanes. My first type of reaction is nucleophilic substitution reaction. Nucleophilic substitution reaction. What is a nucleophile? Species containing negative charge. Substitution is, if my CH4 is there, I am substituting the nucleophile in place of hydrogen like this. I am substituting. I am removing one and I am putting another one. So my nucleophilic substitution reaction is of 2 types here. What are those? That is first order, that is unimolecular substitution reaction and bimolecular substitution reaction, and simply we call it as SN1 and SN2 reactions, wherein this will be 100% asked question, either SN1 or SN2. 100% asked questions in PUC exam for 3 marks or 2 marks. Most probably they'll ask only for 3 marks. What is SN1? What is SN2? We will see it now. We have a separate mechanism for that. We have to study the mechanism. I will erase this. So what is SN1 mechanism and SN2 mechanism? SN1, first of all, when we see the question paper, first write down SN1 is unimolecular. It is unimolecular. N is nucleophilic, S is substitution. Unimolecular nucleophilic substitution reaction. First write down the name. What is the mechanism for this? What is the mechanism for this is the main asked question. How does it undergoes? For example, I have my hydrolysis of tertiary butyl chloride. I have my hydrolysis means adding OH minus. Hydrolysis of tertiary butyl bromide. This is one example. So what happens here is tertiary butyl bromide is C. I have tertiary butyl, it is CH3, and Br. This is tertiary butyl bromide. Why? My bromine atom is attached to that carbon, which is in turn attached to 3 other alkyl groups. So that is tertiary butyl bromide. If I am substituting NaOH with it, I am the reaction is happening with NaOH, Na plus and OH minus it is. So my Br will be substituted and in that place I will have my OH. So this is my tertiary butyl alcohol, OH, right? So it is my tertiary butyl alcohol. This is the first whole reaction. What is the reaction? Full reaction, it is there. How does it happens? What is its mechanism? It is 2-step reaction. How we will see that? Step 1. in my SN1 reaction, step 1 is hydrolysis of tertiary butyl bromide. My step 1 is the mechanism. Step 1, I have my tertiary butyl bromide. Tertiary butyl bromide. First, step 1 is my tertiary butyl bromide undergoes dissociation. My tertiary butyl bromide undergoes dissociation to form planar carbocation. Planar carbocation means my bromine is removed from the tertiary butyl bromide to form a planar carbocation. Carbocation means it is having plus charge on it. So the first step, the explanation should be written here. The tertiary butyl bromide undergoes dissociation to form planar carbocation, that is tertiary planar carbocation, which is stable. It is stable. It is stable always. It is stable. This is step 1. This is my step 1. What is step 2 now? What is step 2 now is, my step 2 is this carbocation so formed in my step 1. The carbocation so formed, my plus charge should be there upon the carbon atom only. So thus the formed carbocation, stable carbocation, is attacked by OH minus, so opposite charges attract, and my tertiary butyl alcohol is formed. Thus OH is attacked and my tertiary butyl alcohol is formed. So that is step 1 and this is step 2. This itself is the reaction of unimolecular nucleophilic substitution. This is SN1 mechanism. So what is unimolecular SN1 SN2 is my reaction. This unimolecular nucleophilic substitution reaction, it depends upon the concentration of alkyl halide I am adding. It depends only upon the concentration of alkyl halide. I don't mind with this concentration, how much I add, that is left to us. That doesn't depend the reaction. So how much I am adding, the alkyl halide only matters a lot. So as it depends only upon one reactant, therefore it is unimolecular nucleophilic substitution reaction. So it is SN1 reaction. Next we will go further with SN2, and one more thing here, it is first order reaction. This SN1 reaction is first order reaction. What is first order, what is second order? We will learn that in chemical kinetics chapter. So we will move forward with our SN2 mechanism here in the next moving forward. Today some problem with my marker, please adjust. So my next is SN2 mechanism. What is SN2? As soon as I see that, I am writing the name, bimolecular nucleophilic substitution reaction. I am writing the name first. And my SN2 reaction is very easy and it takes place in only one step. How does it takes place? Now see it here. There we saw that hydrolysis of tertiary butyl bromide, but here I am seeing hydrolysis of methyl bromide. It is methyl bromide. CH3Br, it is methyl bromide. What happens in SN2? My nucleophile, as it is nucleophilic substitution reaction, my nucleophile attacks the carbon atom from backside. Attacks the carbon atom from backside, which follows with a intermediate state. Intermediate state where inversion of the structure takes place. It gets inverted. How it gets inverted? My two hydrogens, these two hydrogens come here now. My two hydrogens come here now. One more hydrogen goes up, and there will be a partial breaking bond. I am not writing a straight line, I am writing it in a dotted line. There will be a partial breaking bond between the CBr and partial developing bond between C and nucleophile. This is intermediate state. I am putting a bracket 100% here. It is intermediate state. This is my intermediate, where the reaction takes place, where nucleophile attacks my carbon from backside, and there follows the intermediate state where there will be a partially breaking bond with the bromine atom and partially developing bond with nucleophile with the inversion of structure, and that inversion we call it as Walden inversion. We call it as Walden inversion, and this the reaction follows, and my bromine goes off and my nucleophile gets added up, forming a normal structure now. So this is SN2 mechanism, that is bimolecular nucleophilic substitution reaction. Now my reaction, SN2 reaction, a note, small note, my SN2 reaction depends upon the concentration of both haloalkane and my nucleophile. It depends upon the concentration of both haloalkane and nucleophile. Therefore it is bimolecular 2. Therefore my order of the reaction is 2. It is second order reaction. It is second order reaction. It is second order reaction, SN2 reaction. So a major difference between SN1 and SN2 is, that is first order, then it is second order, then here it is the inversion of structure doesn't take place, but SN2 the inversion of structure takes place. And one more thing is SN1 reaction. SN1 reaction is favored by polar solvents, where there is separation of charge, where my H2O, like H2O for example I am telling, it breaks as H plus OH minus. There is separation of charges, so itself it is a polar solvent, like that. Separation of charges should be there. So SN1 is favored by polar solvents, SN2 is favored by non-polar solvents. This is a major difference. So this is about the SN1 and SN2 reactions of haloalkanes. Moving forward with my next reaction, that is elimination reaction. Nucleophilic. After nucleophilic, I am moving forward with my elimination reactions. What is elimination reactions? Yeah. What are elimination reaction? I am eliminating a thing in that reaction. What are elimination reaction? In that first is beta elimination reaction.
It is beta elimination reaction, where it is very important, and it follows Zaitsev's rule. This spelling is uh, different in different textbooks, but what I have studied, that I am telling it here. It follows Zaitsev's rule. It follows Zaitsev's rule. What is that Zaitsev's rule? What is the reaction? We will see that with an example. With an example, we will see that. So I have my molecule like this: CH3, CH3, CH2, CHBr, CH3. I have my molecule like this: CH3, CH2, CHBr, CH3. This is butane, that is 4C, and bromine atom. So bromobutane it is. I am adding this with alcoholic KOH, alcoholic potash it is. What happens here is, I want my Zaitsev's rule. What is Zaitsev's rule is, a product will be formed where, see here, I will write the product now: CH3, CH, double bond CH, single bond CH3. This is my major product formed. Major product formed, plus I will have my one more product like this: CH3, CH2, single bond CH, double bond CH2. 2 3 4, yes, 1 2 3 4, yes. This is minor product. Why this is major, why this is minor is, my double bond, according to Zaitsev's rule, it is very important. My double bond so formed in the result of the reaction will be formed, double bond will be formed where there are equal number of alkyl groups to its left and to its right. To its left and to its right, there should be same number of alkyl groups. Here I have 2 alkyl groups, here I have 2 alkyl groups, but here I have only one alkyl group here, and here I have 3 alkyl groups here. So therefore it becomes minor product according to Zaitsev's rule. Zaitsev's rule tells me that the bromine atom, this is alpha carbon, the halogen attached carbon will be my alpha carbon, this is beta carbon, and this is beta hydrogen. So my beta hydrogen will be removed and a double bond will be formed here, and the alpha halogen atom will be removed. So that is Zaitsev's rule. Zaitsev's rule tells me that the double bond formed in the reaction will be in between the same number of alkyl groups to its left and to its right. Zaitsev's rule, I think it is clear. So the double bond formed will be formed in place where there are equal number of alkyl groups to its left and right. That is Zaitsev's rule. This is beta elimination reaction, that is elimination reaction. The next reaction is reduction reaction, where it is reduces. What is reduction? We all know that. So reduction reaction, I am changing my pen. So reductional reaction, my third type of reaction. First one was nucleophilic, second one was elimination, and the third one is reduction, where I have my reducing agents like this. I am writing just the reaction which is useful: C2H5Br plus H2 in presence of nickel, where at 575 Kelvin, 575 Kelvin will yield me C2H6 plus HBr. It is a hydrocarbon molecule. And I have one more
like this, C2H5I plus Hi in presence of red phosphorus in 450 Kelvin. I have to provide it with certain conditions. So will yield me C2H6 plus I2. This is my reductional reaction. So there it gets reduced here. What gets reduced? My means here in this case of haloalkanes, my hydrogen gets added. So that is reductional reaction. Here it is 5, here it is 6, but there will be having some oxidation states that we'll study it later. So this is reduction reaction. Next type of reactions that we are going to study is reaction with metals. Very important reactions are lining up now. So reaction with metals, that is fourth one. That is reaction with metals. Many important reactions are there on way. We will study the first reaction, that is Wood's reaction, which is very important for both of my first PU as well as second PU. So this is Wood's reaction, a simple reaction where my 2Rx, that is Rx, the haloalkane, plus 2Na plus Rx. I am writing it in a way that is very easier for us. In presence of dry ether medium, this, if it is not there, 100% they are going to cut marks. If dry ether is not there, the reaction itself will not take place, like that will not take place. So my reaction proceeds further with formation of RR, higher hydrocarbon chain, with 2NaX. This is my reaction. For example, to see Rx, I am taking CH3Br plus 2Na plus CH3Br, that is methyl bromide, in presence of, it is in presence of dry ether. In presence of dry ether, I am having CH3, I am getting higher hydrocarbon chain plus 2 NaBr. This is ethane, 2 carbon, so it is ethane. This is Wood's reaction, which is very important. Next follows my Wood's fatigue reaction. What is it? We will see it now. Next follows my sorry, a small technical error. So next follows my Wood's fatigue reaction. What is Wood's fatigue reaction? We just saw Wood's reaction. Next is Wood's fatigue reaction. In that, be Wood's fatigue reaction. Only fatigue reaction comes in my haloarenes. Only fatigue reaction comes in haloarenes. Now I will see my Wood's fatigue reaction, wherein my Rx will differ here. Rx plus 2Na plus R dash X. Same, in presence of dry ether, I will get R dash plus 2NaX. My R will be alkyl group. My R dash will be aryl group, that is containing a benzene ring. For example, to see in this Rx, that is CH3Br, I will take plus 2Na plus, this is haloarene. We will see it in next coming classes. In presence of dry ether, I will be getting a molecule like this. What is this? We will see later. CH3 attached to a benzene ring plus 2Na Br. This is my reaction. Woods fatigue reaction. The second reaction. This is very important reaction. Let's proceed with the next reaction, that is with sodium. This is with sodium. Next is my magnesium, a very important reaction with magnesium, that is C reaction under with metals. When my RX react with Mg in presence of dry ether medium, this is the product formed will be of new name for us. So this is Rx plus Mg. Rx plus Mg in presence of dry ether will yield me RmGx, a very important compound which is known as Grignard reagent. A chemistry student learning first PU and second PU, if awakened from sleep, also should tell what is RmGx. This is Grignard reagent. RmGx is Grignard reagent. For example, to see, I will take here C2H5Br plus Mg. Dry ether in presence of dry ether is very important. In presence of dry ether, I will get C2H5MgBr. So this will be used as a reagent to prepare many compounds. We will come across in many compounds such as aldehydes and ketones, their preparation we will see in that chapter. So this is formation of Grignard reagents. So first we saw reaction with metal, that is Woods reaction, then Woods fatigue and Grignard reagent, formation of Grignard reagent reaction. So this finishes my haloalkanes. This finishes your haloalkanes, that is alkyl halides with its chemical reactions. We'll see about haloarenes in our next video.